welcome to another lesson. I'm going to try to get right into it with Unit 9, Exponential and Logarithmic Functions. In shorthand, we call them logs. And I'm going to try to make this as no nonsense as possible because all the rest of these videos are going to be recorded. So I'll try to make this quick, okay? I'll try to make it as painless as I can. Let's get started. So first of all, a logarithm, what the heck is that? A logarithm is an exponent. It's just another way of writing exponents. So for example, if we're asked to solve the equation 2 to the power of x is 8, or the question, to what power do we raise 2 to get 8? Or 2 to the power of something is what? Well, if we know that 2 to the power of something is 8, it's a way of finding that mysterious value, right? And of course, you should be able to figure out that that's 3. So technically the answer would be 3. So the answer is 3 because 2 times 2 times 2 is 8, or 2 cubed is 8. Instead of asking that question, we can say, what is log base 2 of 8? And the answer is still 3. So in other words, you could say log base 2 of 8 equals some x. It means if we take 2 raised to what power is 8? It's the exact same thing as saying 2 raised to some power is 8, okay? So they are the equivalent expressions. They just have two different forms. Exponential form is this one. So the base raised to an exponent is a number. And the logarithmic form, where we have log with a base and then a number equals an exponent. So one nice thing to keep in mind is that the base of the logarithm is the same as the base of an exponent. And let me make that clear to you, but you can see it here, the base of this logarithm, the little number on the bottom of the log, is also going to be the same number as we have on the bottom of the exponent. In fact, we can change between them freely depending on what we're trying to do. So two quick notes. Logs are not defined for negatives. Log of a -3, not possible, doesn't exist. And secondly, logarithms are only defined when the base is positive and not equal to 1. So that means we can have log of 2 of something, we can have log of 3 or, 12 of something, but log of 1 of something is not okay, and certainly log of any negative number is not okay. Let's do some examples. Convert the following from exponential form to logarithmic form. From exponential to logarithmic. We're going to somehow do this changeover. Just because in the interest of time, I'm going to make this as easy to understand as possible. If you have a base to a power, and you have, 5 squared equals 25, say the same thing as a log, this is what I recommend you do. Take the base, bring it over here, and it's going to become the base of a log. The 2 comes down, you have a log with that 5 as its base, and it equals 25. Okay, let me give you another version of that. What if it was 25 equals 5 squared? Well, once again, take the base, bring it over to the other side, and make it a base of a log if it's not already a log, and the 2 comes down. So once again, log base 5 of 25 equals 2. That 2 here comes down here. Let's get some more practice. Question 2. The answer for this one, well, we see that this is the base. We know it's a base because, again, it's something raised to a -2. That's our base, our bottom number. Bring it over here, make it the base of a log, and bring this -2 down. So the -2 pops down. We end up with log base 3 of 1 over 9. You can choose to put those brackets in or not. I choose to use them because it makes it clear, but many students just write this. It's up to you what you choose. And that's the final answer. That's done. It means 3 to the power of 1 over 9 would be -2. Sorry, 3 to the power of -2 would be 1 over 9. Same thing here. What do you think we're going to get? I'll just write it out for you. And there we have it. It means that 4 raised to a 3 gives 64. Let's try the other examples. It's the same thing, but we're just going backwards, okay? So I recommend you give them a shot. Pause the video and see if you can get them first. Let's just jump right into it. In the interest of time, I'm going to do them quick. So in this case, the only difference is that we have the log of the base instead of an exponent, but that's easy. By the way, we're trying to convert, in this case, from logarithmic to exponential form. So it's currently in log form. We need to make it in exponent form. Just bring it over here. Make sure it stays a base. So the 64 stays where it is. You can almost think of the log as being canceled now. And the 4 is now a base. A base of what? A base of an exponent. And you can always check that. What is 4 to the power of 3? It is 64. Check it on a calculator. Next question. We'll take the other one there so you can see it too. Log base 7 of some crazy thing. Well, you don't even need to worry about what it is. Let's just move it over and we can get what the equivalent exponent form is going to be. 7 is our base. Negative 2 comes up as a power, and we're done. Final question. 27 is our base. Bring it over here as the power of an exponent. Remember, you can kind of think of these logs as disappearing now. 3 equals 27 as a base to the power of 1/3, which of course is correct. The cube root of 27 is 3. So long story short, if you want to know why this rule works, it's because of this. We know that b to the power of e is n. We also know that log to the power of b of some number is an exponent. So those rules are equivalent, exponent form and logarithmic form. Take the base, bring it over here, what do you get? You get e equals b to the power of n. Sorry, log b to the power of n, which is this. Let's try the other way. Take the base, move it over here, get rid of the log. It's a base to the power of an exponent. Hey, that's what we have here. So these rules definitely work. They definitely tell us what we need to get, and that's why they work. That's why we can use this trick, because it works every time. Let's move on to page 2. Page 2 starts out with this table, and it tries to compare laws of exponents to laws of logarithms. And you can pick through this table and try to make sense of these rules, but I find it a little easier to break the rules down in a little different way. So the way that I approach this is the same way that I found it on Khan Academy one time, and you can follow this QR code. Just scan it with your phone using a QR reader app, and it will bring you to a website. But the main rules are as follows. There's a product rule and a quotient rule and a power rule for logs. And what it says is that if you have two of the same base of logs, and they have things inside of them, they can be combined into one big log of that base. All right, as long as it's the same base, you're allowed to do that. And the opposite is true as well. You can split them into two different logs, kind of just like what we were doing with the radicals in a way, or especially like we deal with exponents, right? If they have the same base and they're multiplied, you can add the exponents. So same thing with the quotient rule. You have the same base. As long as they're the same base, you can be split into two logs. With a subtraction, notice if it's product, you get an addition out of it, just like when you do exponents. Quotient, you get a subtraction out of it. And then this power rule, which we won't quite see yet, but you'll see it soon, as long as you have the same, actually there's no different base here, so I don't need to mention that. You can take the power of whatever's inside and bring it down in front. And you'll notice it comes in front of the log and it gets rid of it. So that's kind of an easier way to deal with this stuff. And if it comes up later, I'll probably call it the power rule. So let's actually use the rules, okay? We want to write each expression as the sum or a difference of logs. Well, in the first case here, this is a product. So we're going to use the product rule for logs. What that means is you can split the single product of 7 times y into the log base 5 of 7 plus the log base 5 of x. And that's all there is to it. You should try and pause the video and try number 2. Number 2 is the exact same method, it just looks different. The thing is, t squared is t times t, so it is a product, which means we can split this log up into two pieces. Since it's a product inside, it can be the log base 4 of t plus the log base 4 of t. And again, you don't need to put the brackets in. A lot of teachers just write, for example, log base 4 t, and so on, but I like to put the brackets in, at least when we're first learning it, so that you know there's definitely something inside that log. It's not multiplied by it. Okay? So that's it for product, and just remember that product rule is what gives us our pluses. Quotient rule, which is the next piece is going to be, you see there's quotients or fractions inside. You're going to be dealing with minuses, okay? So let's see if we can figure that out. Pause the video, see if you can figure this one out without my help. I see that it's a quotient inside, so it's the log of the first one. You can say subtract the log of the second one. That's all there is to it. Pause the video, see if you can get number 4 on your own, or at least try it before I do it. Number 4 is a mix. We actually have a product on top and a big quotient on bottom, right? So let's split it into 2 pieces so you can see it clearly. This is log base 2 of AB minus the log base 2 of c squared. So there's something interesting going on here. We've got our log of AB, that gives us this piece. Got a log of c squared, that gives us this piece. But these are both products in themselves, so we can split them up even further. We've got the log base 2 of A plus the log base 2 of B minus, and I actually showed you that product rule before, which I'll go back and fix a previous question. Look what happens here. We can use the power rule. We can split it into 2 logs, but it's actually easier if we use this sneaky little log rule to bring the 2 down. And then we can remove the power from the c. Okay. So if you have a keen eye, you can actually see that I should have done the same thing in question 2. Because look, this question is not finished. I've got log base 4 of t, log base 4 of t. I've got 2 log base 4 of t's, which could have been done by the power rule. So for this question, could use the power rule. And I'll very quickly write out what that would look like if I had done the power rule, okay? Same exact answer. So hopefully you're making some sense of this. Basically, there's 3 rules. There's the product rule, there's the power rule, and there's the quotient rule. And they all are fairly straightforward. They're just probably new to you. Or maybe for some of you it's not so new. But once again, scan this QR code and see if you can make some sense of this. Let's do the end of page 2. It says we need to write them as a single logarithm. This is the exact same thing as we just did, just backwards. So they have the same base for number 1. That means we can combine them. They're currently added, so you can combine them into one big log, and it's 5 times 6. Remember, this is the product rule, just done a different way. 5 times 6 is 30. So you might be thinking, hey, that's a whole lot like what we did with the radicals. Remember when they have the same radical? And you would be right. So I'm going to put a little note here. And maybe you can see what the relationship is. If it was square roots, it would be root 30. If the logs are the same, we get a similar situation going on. Just take some time to think about that, okay? For 2, what are we going to get? Maybe pause the video, give that a shot. We're going to be using a few different rules. Power rule, and product rule and quotient rule. So we have the same log for all of them. We know we can combine the first 2. We could do this in one big step, but I'm going to do it in 2 steps. Log base 6, x and 7 get combined, minus log base 6 of 5. Now we have the same log again. Look, log base 6, log base 6, but we've got the subtraction. So here we can do the quotient rule. And our answer's done. Okay, so we could have skipped directly to the final step. The reason I know you can do that, or the reason I'm telling you can do that, is you can do the product rule first, take that full expression, and then put this on the denominator. So literally you could skip straight from the first step to the last, if you wanted to. Let's move on to page 3. So on this page we need to evaluate logarithmic expressions, and really it's going to be a lot of calculator work, which is going to be a good news to a lot of you. So it says we need to find common, and we need to find natural logarithms. So what it says here, it says, although we can find a logarithm of a number for any positive base, except for 1, the most commonly used bases are 10 and e. The common logarithm has a base of 10, so logarithms to base 10 are called common logarithms. When we write log x, we mean log 10. Very important. If you had e, a base of e, logarithms to base e are called natural logarithms. When we write ln of x, we mean log base e of x. And I did skip a little point in this. It says whenever log is written without a base, it's assumed to be 10. Your calculator automatically assumes this when you use the log function. Let me show you what it means. If you were using a Casio and you click the log button, it doesn't even give you a base. You just say log of 5 and go about your merry business. That assumes that it's log of base 10. If you wanted a different log, you would have to do something a little differently. Thankfully on this calculator it's very easy. If it's a log with a different base, your number is right up here. Log base 5, for example, of 25, it'll give a 2. Okay, great. What if you wanted to do the same thing on the TI-83 or the TI-84? Well, that's not too difficult either. You'll bring up the TI-83, or have it in your hand, and the log button is down here, log of 5. Okay, that's what it is. If it was natural log, the log button is right there. And if you wanted a different base, on the TI-83 or TI-84, it's a little different. You got to have Math A. You got to click Math A. What I mean by that is you click Math, and it's under A. So you got to go all the way down to A. There's a quick way to do it. You can go Math and then Alpha to get into your letters, and then hit Math again. So Math, Alpha Math will give you this. On the TI-84, it's got a really nice display. It'll just be real nice and simple for you. On the TI-83, I think it's a slightly older method. I'm not even positive it has this method in there, but there's definitely a way to do it, but this is how I would recommend you do it. So let's do some examples involving the calculator. Find whatever way works for you to put these into the calculator, and make sure you can get the following numbers. Log of 100 is 2. Log of 48 is 1.68. Log of -5, it's going to give you some sort of error because you can't get negatives. So that's something you should keep in mind. By the way, this one, think of it this way, right? It's log, technically base 10 of 100. It's like what power does 10 need to have to make 100? It will be 10 squared is 100, which means that our x is 2. So just if you're thinking about it that way, you can, but the calculator is much easier. And as soon as you get things like this, you're not going to be able to do it without a calculator anyway. So just keep the calculator in handy. Natural logarithms in the calculator is just the ln button, ln button. That means we have a log with a base e. Most calculators have it. Ln, you just put your number in. So in this case, ln 19.3, close the bracket, 2.96. Try the same thing for the next one. You get 3.23. 2 decimal places is fine. Put in the next one, you're going to get a negative answer. It's okay if you get a negative answer, you just can't put negatives into the log in the first place. Let's move on to page 4. So at the top of page 4, it gives us this formula. It's called the change of base formula. And it's called the change of base formula because it makes us, or allows us, to take a log of base A, of some number B, and break it into 2 pieces. So for example, if you had log, let's just say log base 5 of our 25, like we saw before. Think of it this way, the base stays on bottom, so the 5 becomes log 5, and the number stays on top. So there's a lot of this idea of the base staying low. So for exponents, it's the base still. This 5 ends up being on bottom. You kind of split this into log 5 and then log of 25. But really, you should just use your calculator. If you have the Casio, the function is where I showed it was before, so log base 2 of 64, for example, gives this. So it's a 6. And the TI-83, TI-84 are very similar. If you can't get it on your TI-84, for example, maybe that function isn't there, you would have to write something like this. You'd have to just use the change of base formula, log of base 7 over log of base 3, and your calculator can definitely do that, and you'd get the answer 1.77. You know, you can try number 3 on your own. Pause the video at any time, in fact. Try to get these. But the answer here, if you work it out, is 1.88. And that's all there is to it, really. The next topic is no more difficult. So objective 9.33, use a calculator to find anti-logarithms. So it says, suppose we have the common logarithm of a number. Common logarithm, do you remember what that means? It means log base 10. And we want to find the number itself. This process is known as finding the anti-logarithm, or anti-log. First, we convert to exponential form, then use the 10 to the power of x key on the calculator to determine the number. The reason this works is because if you think about what the natural log is, okay, it's got this hidden 10. There's a base of 10 there that you just can't see. So our formula, when we bring that over, if you remember from earlier, that cancels out the log. We get n equals 10 to the power of 1.35. If you remember that, if you know how to change your base around or know how to change to exponential form, that's easy. Literally put this into your calculator and you'll be fine. So n equals 22.39. And there are a few ways to accomplish that. So once again, I'll go to my handy Casio. Maybe you see the 10, so 10 and your power button on the Casio is right here. You get 1.35. That's 22.39. There is a built-in natural logarithm or anti-log function. It's hidden behind the log here. Just go shift log. It knows they're related, so it just gives you the 10 right up. And 1.35, and you got your answer. On the TI-84 or TI-83, the process is similar. The TI-83 knows that logs and anti-logs are related to each other, so you just press second log, and you'll get into your 10 power menu, and you've got 1.35, and you should get your 22.39. If you can't figure that out, or if you're having trouble with finding the functions on your calculator, just let me know, okay? Send me an email and just say I'd like some extra help figuring out my calculator, or type in TI-83 logarithms into Google or something similar, YouTube for example, and there should be lots of really good tutorials, but I'm happy to do that for you if you like. So I'll do the second one here for you. Once again, in my brain I know that logs are actually base 10, so n is going to be 10 to the power of 0.929, right? For the same reason as before. Hit your anti-log button, put that into your calculator, you're going to get 8.49. And if you don't, let me know, because that means I've made a mistake. Let's move on. Notice that those examples we just did were based on common logarithms. If we're given the natural logarithm, where we have the base e, it's a very similar process. Instead of pressing the ln button, you press the shift ln, or instead of the natural ln, let me show you what I mean. The calculators know that these things are related. You've got ln on one side, and if you press shift, you've got e on the other side. They are telling you what the base of the log is. For your TI-84, same story. Second ln, you got your base e, Bob's your uncle. And as a reminder of why it works, let's not forget that there's actually a base e here on the ln, okay? It's log base e of x. So ln of x is log base e of x, which we can bring the e to the other side as a base and cancel the ln. So you put that in your calculator using the function that I showed you, and you should find out very quickly that this answer is 0.38. Let's try the next one. Try it yourself first. We've got the natural log of x. All we need to do is get the anti-log. So x is e to the power of the right side. Really nice and easy to get it. 19.76. I'll just show it once on the Casio or show it once on the TI-84. You can see that the method's the same on the Casio. Let me move this over here. On the TI-84, you've got ln of x. So just, you know you're dealing with lns. You want the anti-ln. It's kind of like the inverse tan functions, right? It works very similarly. Inverse ln, or inverse of the natural log, is exponential to the power of 2.9836. Enter. 19.76. Maybe you just can't find that function. Well, if you can find e, which is over here, so second e, you can hit the exponent button. 2.9836 accomplishes the same thing. Same answer, same method roughly, and you got it. Let's move on to page 5. The purpose of page 5 is to teach you one key skill, and that would be solving exponential equations or logarithmic equations using the same base. So what that means is we're going to see these questions come up, and we're going to match bases. So an exponential equation is one in which a variable occurs in the exponent. So what it means is you're going to see these exponents, the variables in the exponents, which students see that and they're like, are you serious? We have more new stuff to learn? But honestly, this actually comes out pretty quick. The reason it falls apart pretty quickly is it says, an exponential equation in which each side can be expressed in terms of the same base can be solved using the following property. If b to the power of x equals b to the power of y, then x equals y. Or in other words, and this is really what you should be taking away from this, if the bases are the same, set the exponents equal to each other. That's going to help us a lot. Let me show you how it works. Let's jump right into it. The bases are the same here, which means that we can set the exponents equal to each other. Just set those two things equal to each other. 2x plus 1 equals 3x minus 2. Isn't that nice? Now that we have this, we just solve it. And what if you solve this, which is super, super easy really, 3x equals 3 or 3 equals x. Okay, group the like terms on each side and you'll be fine. And then if you wanted to check this, just to prove to yourself that it is correct, put it back into the original expression. 7 to the power of 2x plus 1. What does that equal to? Well, that's 7 to the power of 6 plus 1, so 7 to the power of 7. That's all good. I'm going to leave it like that for now. I'm going to check the other side. 7 to the power of 3 times 3 plus 1. 3 times 3 is 9 plus 1. Oh, minus 2, sorry. 3 to the power of x. What am I saying? 7 to the power of 3x minus 2 is the same as saying 7 to the power of 3 times 3 minus 2, which is 7 to the power of 9 minus 2, or 7 to the power of 7. So we can see that the left-hand side equals the right-hand side, and we're all good. You don't need to do that check. I just wanted to show you that it is, in fact, equal. Number 2 is a little more involved, although I wouldn't say it's difficult, just, again, a little more involved. The problem is we've got exponents in the powers, but the bases are not the same. Let's make them the same. How are we going to do this? We need to try and find a way to make base 3 on that side as well. We're not going to make base 27 on this side because that would make things complicated. But we can definitely break 27 down into something to the power of 3, can't we? And the reason I know that is that I know 27 is 3 to the power of 3. 27 is a perfect cube. So what that does to help us is the left side I'm going to leave like it is. But on the right side I have 27, which is really 3 to the power of 3 to the power of x. These exponents are going to multiply, so I end up getting nothing changed on the left side. But on the right side, the exponents multiply because the power to a power. I get 3 to the power of 3x. And now my exponents, or I should say my bases, are the same. Which means I can make the powers equal to each other. So 2x minus 1 equals 3x, and now once again it falls apart. I can bring the 2x over to this side if I want to, leave the negative 1 on the other side, and bam! Negative 1 equals x, or x equals negative 1. It doesn't matter what way you write that. Technically you could write it either way. It doesn't make a difference. If you check that, you should see that the left side equals to the right side. So hopefully you can see the difference between those two examples. And ultimately we're just trying to make the bases the same. Let's move on to the next page. This page, which is page 6, is just a bunch of extra examples. So I'm going to say try these yourself. I'm going to write out the answers here with very little explanation because I want you to be able to try it, and it's basically a lot of the same thing done over and over again. If I feel like I need to further explain myself, I will, but most of these are pretty straightforward. So hang on for the ride. Pause the video here and hang on. I'll put you the answers here so you can check. Here, x equals negative 8 for this one. For this one, x should be 1. For number 5 here, x should be 2. And for 6, x should be negative 2. So go ahead and give those a shot, and I'll do the full solutions now in a minute. So question 6 has a little bit of a weird thing going on. The main thing you need to notice is that if you have a fraction like this, 1 over 16, you can treat it as its own exponent. So what I mean is, flip it, and then we have our negative 1 on the outside, right? 1 over 16, or 16 to the negative 1, if you flip it over, get the reciprocal is 1 over 16, so you can do the opposite operation as well. Kind of the only one in this set that kind of throws you for a loop a little bit, but after you get that step, everything else falls apart. So there we have everything on one page. Please just let me know if you need any of that further explained, but I think once you do enough of these, you can see the process you need to take. Let's try page 7. This page starts by saying case 2. So the previous case of solving exponential equations, which means letters in the exponents, was same bases. And the difference here is that they have different, different bases. So what do? Do we give up? No, we truck on forward and we learn one of the very last things in this entire course. So you're almost there. Hold on for the ride. Not all exponential equations can be expressed in terms of a common base. Like, that's just a fact. Okay? They can't all be expressed in terms of a common base. For these equations, we need to use logarithms. And we're going to be using a lot of the product and quotient and power rule. So if you have a good grasp of your power quotient and power rules, product quotient and power rules, I should say, then this topic's going to be very simple for you. So these are the steps we're going to take to solve most exponential equations. Not every single one, but most of them. First step, isolate the exponential expression. If there are other terms other than the exponential expression, move them to the other side of the equation. The exponential expression, by the way, is this. So if you're wondering, like, what the heck is the exponential expression? It's the expression that has the exponent in it. Okay? That's our first piece of the puzzle. The second step, and probably the most crucial step, is to take the log, take the common log or the natural log of both sides of the equation. And we'll see the difference in terms of if it's natural or common log later. Most of the time, we actually want to use natural log. It's just more common to do so. And third, apply the log rule for exponents. Well, in fact, there are 3 log rules that are really going to be used. Solve for the variable. Let's get started. Let's see what these examples have in store for us, shall we? So following the steps, we need to isolate the exponential expression. Step 1's already done. So we move on to step 2, which is take log of both sides. And I'm going to choose to use natural log because it literally makes no difference. I took the log of both sides. And what that does, what that does is allows us to use our power rule. Logs are really powerful because they have rules that no other types of numbers have. So we take the exponent, we can bring it down in front. That's directly from our power rule. That means we have an x ln 5 is equal to ln of 7. And in order to get to that x, all we need to do is divide both sides by ln 5, just like you would any other number. Cancel, cancel. And hey, look at that. We've got ln 7 over ln 5. Calculate that out, it's 1.21. We showed you how to calculate that previously in the video. Perfect. Nice. Let's move on to the next question and see what we can do. So once again, we have an expression that doesn't have the common base. There's no way that we can put 3 to the power of something. Right? This x can't really do that, can we? It's not a perfect square, it's not a perfect cube. So we really have to isolate this term and then do the ln of both sides. It's already isolated, and so I'm just going to do ln of both sides. Once again, what that allows us to do is to take this whole power and put it down there because of the power rule for logs. So we have 2x plus 1, all multiplied by ln of 3. And ln of 15 on this side. You might be wondering, why the heck are you using ln? Why aren't you using log? No reason. It's ln is shorter to write, and they are ultimately the same thing. I mean, at the end of the day, they have different bases, but they work the same way in terms of the product, quotient, and power rules. And you see lns a lot in your future math courses, so I just want you getting used to it. Anyway, long story short, we need to divide both sides by that ln 3, just like we did last time. That will cancel the ln, and it'll leave this piece on the left, which will be easy to solve for, okay? So we have 2x plus 1 on the left side. On the right side, once again, you can calculate it. It becomes 2.46, and then solve for x like a variable, because it is a variable. Bring the 1 over, subtract it, and then divide both sides by 2. So they're not long questions. They might look complicated, but in terms of some of the other stuff we've done in this course, this is really not that bad. You just need to have a pretty good grasp of your power rules and things like that. So take your time to go back through that and make some sense of it, and I'm going to keep doing some practice. I'm not going to talk through the rest of these practices much. These two questions are very similar. The only difference is that I'm going to need to isolate the variable first, bring it over to the other side, but the rest falls out easily. So I'm not going to talk about it as much. I'm just going to show you how to do it, and hopefully the work will speak for itself. So this next topic is very similar to the previous one. In fact, it's case 3, you'll notice, and then we're going to solve logarithmic equations. So instead of exponential, where we're dealing with equations that have the exponents up top, something like that, I don't know, it doesn't really matter. We're going to be dealing with things like this, which have the variable inside the log instead. So a logarithmic equation can be solved using laws of logarithms. Once again, that really shakes down to product rule, quotient rule, and power rule. That's really what you get out of logs. That's the most important step. You can call them what you want, but really there's 3 big ones. And the steps are as follows, okay? They're similar to what we did in the previous case with exponentials. We have to isolate the logarithmic expression. That's extremely important, meaning the log should be on its own on one side of the equation, kind of like this. This one's done for us. You may need to use the law of logarithms or laws of logarithms to create one log term. We'll see what that means in a second. We need to rewrite it in exponential form. Remember, keeping the same base, just rearranging, and then solving for the variable. Let's see what it looks like. It's actually not that bad. First things first, this first question already has the log term isolated, so we need to rewrite in exponential form. Remember the form. Look, it looks like this. Log to any base of a number. Let me keep it consistent with your notes, actually. Log of any base of some number is going to be equal to its equivalent exponent. What we do is we take the base, bring it up there, gets rid of the log, and the n stays where it is. So we have n equals our base to the power of an exponent. So that is exactly what I can do at the start of this question. I can take our base 5, because it's all under one log, right? It's all one big log term. Bring it over here as a base, and you can cancel out the log term. What that leaves us with on the left side is x plus 1. And on the right side, 5 squared. Now that should be pretty easy to solve. I mean, we've gotten rid of what made this problem complicated. We have x plus 1 on the left, 5 squared is just 25, and take away the 1. You have your 24. Not so bad, huh? Like, not anything to have nightmares about, especially this close to a final exam. So hopefully that made sense to you. Let's try the next question. See if you can figure this one out. This looks weird. Let's see what we're going to do. Is the log term isolated? Well, no, it's not. The first thing you need to do is to isolate the logarithmic term. It's not isolated if I have a 3 here. So what I need to do is I need to be left with just this, okay? The log term is just the blue. The 3 is the problem. It's not isolated. My computer is freaking out, sorry. It's not isolated until we can get rid of that 3. So divide both sides by 3. That's the easiest way to get rid of that. Cancel, cancel. 6 divided by 3 is a 2. So on the left side we're left with log of x plus 4. On the right side we're left with a 2. And then we go through the exact same thing that we went through before. How do we do it? We rewrite it in log form. Don't forget, This is the same as the antilog. So we have a common log. That 10 is going to come up here. It's going to cancel out this log. We end up with x plus 4 is equal to 10 squared. 10 squared is 100. Take away the 4. X must be 96. Not bad, huh? They look complicated. They look like they're going to be a real pain in the butt. But honestly, it's not that bad once you get into it. So the first thing I did was isolate the log term. The second thing I did was to rewrite in exponential form. Exponential form is a base to an exponent equals a number. You know, they can be in either order, it doesn't matter. And finally, our third step was just to solve. Not so bad. Let's move on to page 9. Oh, hello, number 3. Are you here to make me sad? Because you look like something I can't solve right now. Well, thankfully, I would never give you something that you couldn't solve or didn't have the skills to solve. We need to use the product rule to isolate this log. Okay, so product rule. If you use the product rule, you'll be fine. Remember, that can be used to combine two logs of the same base. So we have a log of base 9, we have a log of base 9. They are being added, which means their insides can come together and multiply. So we end up with one big log base 9, and the insides multiply. It's x times x minus 8. It's x squared minus 8x. If you don't believe me, x times 8, x minus 8. Multiply those out, x squared minus 8x. So I have multiplied the insides. The right side I don't touch. It's a 1. Now I've isolated my log term. The second thing I need to do is rewrite in exponential form. Take the 9, bring it over here as a base, cancel out the log. We're left with x squared minus 8x equals 9 to the power of 1, which is just 9. You don't really need to write the 1, but I'll write it there kind of sneakily. Whew! What are we going to do now? X squared minus 8x equals 9. This is a quadratic. Try to factor. So let's get it in quadratic form, standard form. And now you've got all the different rules under the sun that you can try to use to factor this. I'm going to do the easiest method, which would be noticing that this is a equals 1 form. You can do it directly as a trinomial. You could use the quadratic formula, you could complete the square, there's all sorts of crazy things you can do, but I just recommend you do it the easiest way you can, which in this case is factoring it directly. You should see that you can have x minus 9 and x plus 1 will give us these values. If you solve both of these for 0, like we did in the previous unit, this is what you're going to get. 2 answers in this question. So this question's a little bit more involved, but not so bad, right? There is one little hiccup. And the problem with this is, like, the reason that there's a problem here, or the reason there's a hiccup in the words that I used, is that we're not allowed to use x equals negative 1. And the reason we're not allowed to use that is as follows. So, why? Well, because if we were to check it, and we only need this part, we're not allowed to have the log of negative numbers. If you put a log with a negative inside, you get an error. They don't exist. So I said that earlier in the unit, you are not allowed to put negatives into a log. So just keep that in mind. That probably won't come up too much, but it is something that you should at least store in your memory back there somewhere and be able to call on when needed. Who knows, it could be a multiple choice. You never know where these things are going to crop up. So just try to internalize that. Let's move on to question 4. As usual, I recommend that maybe you try this one first. You should see that x comes out to be 1 over 2. And it involves a quotient rule, but otherwise it's very similar to the previous question. Let's get started. So they are separate logs right now. We can't isolate it into one log term until we use a quotient rule. So I'm going to do that. Quotient rule. Why am I allowed to do that? A couple things. They have the same base, and I notice that there's a subtraction between them, so I can bring them all into one big log as a fraction. So log base 3, first term goes on top, divided by second term on bottom. Equals 2. I shouldn't have put an equal sign on the left side. All right, I've taken the first term. I'll color code if you need to. Took the first term, second term, and there you go. Now that we've isolated the log term, it doesn't look like it's simplified, but we have one big log term on the left. We can take the base, oops, rewrite it. I don't know why it's deleting. My family is falling apart outside my door, sorry. Exponential form once again. Cancel out the log, rewrite it. On the left side, we're left with x plus 4 all over x. On the right side, we're left with 9. Why are we left with 9? Because on the right side, really, when the 3 came over, it pushed the 2 up and became 3 squared. And that's 9, which is why that 9 is coming out of here. All right, so you can try that on your own if you want. How do we get to that 9? It looks like we're pretty much stuck. Thankfully, we're not. We just multiply both sides real quick by the LCD, which is just the x. So multiply both sides by x. It cancels it off the left side and adds it to the right. 9x. Bring the x over. Divide both sides by 8. And we have our 1 over 2. Once again, not so bad once you see it, but it's something that you really need to take some practice with to get used to the different log rules. We've got one more on this page, so we might as well finish it while we're at it, and then we'll go on to the very last page of the entire course. What we've got here are 2 logs, actually 3 logs. What are we going to do? Log 5, log 5, log 5. What do we do with this? Turns out there's a bunch of different ways we can handle this. I'm going to handle this the way that I've handled all the other ones, and then I'm going to show you a second method. So you can choose which one you like. So first I'm going to do method 1, and then after I finish method 1, I'll try method 2 over here somewhere. And at the end of it, you can choose which one you like. So the first way is to combine all our terms. So I'm going to bring everything to the left side. I have log 5 x minus 3 plus log base 5 of x minus log base 5 of 10. And that'll leave the left side 0. That's okay because at least I've got all my logs on one side. Now I'm going to use my product rule and my quotient rule. So I'm going to use for this, I'm going to use my product rule. And then afterwards, I'm going to add in my quotient rule. Why am I allowed to use them? Well, because they're the same logs with the same base, and I've got pluses and minuses. So if I combine the first 2 as the product rule, multiply them, x minus 3 and x, you get x squared minus 3x. The 10 term goes on bottom because of the quotient rule. Now what I need to do is convert it to exponential form. So bring it over here, cancel the log. That becomes 5 to the power of 0, which is 1. So again, because of the exponential form, 5 to the power of 0 is what I get out of this coming together. 5 to the power of 0, anything to the power of 0 is 1, which is why I got the 1 here on the right side. Continue to solve this, so I'm going to multiply both sides by 10 to get rid of that fraction. Cancel, cancel. X squared minus 3x equals 10. We're going to factor this like we did in the previous question. Can that factor? 2 numbers that multiply to make 10, add to make negative 3? Sure can. That would be minus 5 and plus 2. Finally giving us x equals 5 and x equals negative 2. So this is a longer method. It's a bunch of steps. I wouldn't call it difficult compared to some of the things you've been needing to do in this course, but certainly longer than what the next method is I'm going to show you. So that would be method 1. Method 2, let me rewrite the question first so that we can zoom in a little. Okay, the same question, obviously, just rewritten. What we can do is, first off, use the product rule on this side. Okay? Product rule for logs, and see what we get. So that's what we would get on the left side. You just multiply them together, and this is what you see. On the right side, nothing changes, because it's already as simple as it can get. And then we can use the idea that we have the same log on left side and right side. And if you see that that's the case, and this is a rare situation where you're allowed to do this, you can actually just cancel the logs. And the reason for that comes from the same idea that we had with the exponents. So for example, if you had, 2 to the power of x plus 1 equals 2 to the power of 5, well, if the bases are the same, you can make the powers equal. So for example, the bases are the same, you can essentially just think of it as being x plus 1 and 5. Well, the exact same thing would play out for logs. If we had log of x plus 1 equal log of 5, because of the relationship between logs and exponents, turns out just like you can essentially cancel out the 2's and keep the rest, you can essentially cancel out the logs and keep the rest. So just something to be aware of. What this lets us do is essentially skip a step. We get x squared minus 3x equals 10, which if we bring it to the other side gives this. And, we're already back on track with the other method with a little less work. See where I am now? I ended up at this stage, which is a stage that I had from the other method, but I was able to skip some work, right? And the rest shakes out the exact same way. At the end of the day, it's still x minus 5 and x plus 2. They still solve out to be x equals 5 and x equals negative 2. But a very different way of getting the same answer. So as is always the case, or often the case with math, there's more than one way to do things. And that's okay. Just choose a method that works the best for you, or even if you find a third method or a fourth method online that you like better than this, feel free to use it. I'll always look through your work, and if I have any questions about it, I'll just get back to you. But that's it for page 9. Let's do one more question, or at least one more page, and we'll be done this whole course. And you guessed it, page 10 is word problems. Everybody's favorite type of problem, right? Let's get to it. The temperature T in Celsius of a cooling gold bar is given by T equals 22 plus 98 times, this expression, where T is the time in minutes. How long will it take for the bar to cool to 35 degrees Celsius? So we're given two pieces of information. We're given the time, well, we're actually asked for the time, how long will it take? And it says to cool to 35 degrees Celsius, 35 degrees Celsius is our temperature. So we've been given our two things, what we're looking for, and our givens. Let's write out our formula with T included. So that's our given temperature, 35. This is an exponential expression, also known as an exponential equation because it's equal to something. We need to isolate this term. We need to get this term on its own because that's the term that has the exponent in it. Once you get to this point, you're going to want to divide both sides. Oh, that's not 23, that's 13. Divide both sides by the 98. Why is that? Because really we want to get to just the exponential term. So let me make that clear. We need to isolate this without the 98. So divide both sides by 98. What that gives us is 0.1327 on the left. And on the right side, nothing really changed. On the left side, some students prefer to keep the fraction. There's nothing wrong with that. Not log. 13 over 98. You can keep it there as long as you like, but it's up to you. Now that we have the exponential term isolated, this term, do you remember what we need to do? we need to get the log of both sides. Doesn't really matter which one you go for. I'm going to go for the log, and because I'm going to need to solve it, and let's see what we get. Why did I do the log? Because I want to bring this term down because of the power rule. The left side would be negative 0.8771. The right side will be 0.20t. Log of 0.3 is negative 0.5229. And essentially this is like a physics problem now. You're trying to solve for that t term. If you solve that all around, move everything around, this is what you should get. 8.39, it's actually not in seconds, it's in minutes. So all I did, by the way, was I multiplied these two together and then divided it out. Took this and divided it by those two things and got my t. That's all there is to it. So that question looks a little bit weird. I know that it looks like there's a lot going on, but if you are careful, you'll see it's very similar to the question we did earlier with exponential form. Now let's move on to the very last question of the unit. I know I keep repeating that we're near the end of the unit. Well, it's a big deal. So why not repeat it, right? It's important. Now we have this formula that we've been given for the question, and I have a feeling we're going to need to solve something in this formula. So let's see what we're given. Take a minute to read this, pause the video and see what each variable represents. It says a $1,000 investment, which is P, is made in a trust fund at an annual rate of 6%. That's our annual rate, R, expressed as a decimal. Compounded monthly. If it's compounded monthly, if you read this, it says number of times interest is compounded annually. If it's monthly, it means 12 times a year, so 12. Remember, monthly, how many times it's done annually. In a year, there's 12 months every month, so n is 12 years. 12 months. How long will it take the investment to grow? So the value, how long will it take the investment to grow to $3,000? The value is 3,000. We're looking for the amount of time that would take. So we actually have all of our variables, don't we? We have P, we have R, we have N, N's also in here, and we have V. And we're looking for T, so that's the pain in the butt, is that it's exponential form. We're going to be missing something that's in a power, which means we're almost definitely going to be using logs here. So let's work this out and see what we can get. I'll put all the given information in. So once again, we're going to try to isolate everything that touches the power. So work out that bracket, all that sort of thing. Right away, I see that there is a 1,000. I can divide both sides by the 1,000. It's the fastest way to get rid of that. That just works out to be 3. I'm going to simplify this because it's all fractions and decimals. I'm just going to get an equivalent decimal expression for it, which is 1.005. You can keep it as a fraction if you like. I prefer to work with decimals, especially because this isn't really a pure math problem. This is working with money, and they have decimals anyways. So it's not a really big deal. You're allowed to use decimals here. And what are you going to do? If you have the exponent on the top, you're going to get the ln of both sides, or log of both sides. You might wonder why I'm using log and not ln. Well, it doesn't matter. You can use ln, natural log, as long as you apply it to both sides, your final answer is going to work out. I'm just choosing to show you log this time. I could have just as easily used ln, and it would work out the same way. So this gives us log of 3 equals the log of this whole side here. Remember, the reason we're doing this is that it'll let me use my power rule. Power can then come down in front. That's the real magic of this method, okay? Left side I'm going to keep as it is for now. Right side will be 12t times log of 1.005. I'll continue the work over here. Just to make it crystal clear, I might as well make it clear at the very end here. What we can do is simplify the left, simplify the right. Doesn't really matter what way you do it, we're going to get the same answer, but I'll just show you one method. Log of 3, if you want to go with the decimal method, 0.4771, that's the 4 decimal places. Now I'm going to multiply 12 times log of 1.005, 1.005. That will give me 0.02599, so I'll just say 60, and all I have left is that t. Divide both sides, and if I didn't make any mistakes, this is the very end, and I did not make a mistake. 18.35 years. Okay, fancy. So hopefully that wasn't too overwhelming. I know this is a long video, but it's a week's worth of classes really in one video. Take your time with it. Obviously you're at the end now, so it's too late to say that. But yeah, hopefully it made some sort of sense. We do still have a full week as of the time of posting for you to get in contact with me before the exam. Please take advantage of that. And other than that, good luck. It was a pleasure teaching you, and hopefully we'll see you again soon. Take care of yourself.